Hey guys, we are back and we are ready to roll with section 2 of chapter 8, 8.2, adding and subtracting rational expressions. So section 1, we saw multiplying, dividing, how we could factor, how we could cancel. Adding and subtracting works the same way as adding and subtracting normal fractions, which is to say, and I'm going to highlight it right here, whenever we're adding or subtracting rational expressions, we need a common denominator. That should be pretty ingrained in your head by now. So before we get there to seeing some actual adding and subtracting problems, I want to talk a little bit about the LCM, least common multiple of two expressions. So to start, we're going to just look at numbers. Find the least common multiple of 15 and 50. That means, what is a multiple of 15? Well, 15, 30, 45, 60, 75, anything that is 15 times some positive integer, some natural number. What are the multiples of 50? 50, 100, 150, 200, 250, 300. I want to know what is the least common multiple. What multiple do they share? And we want the lowest one. Now, one way to do this would be to say, okay, well, 15 has 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, 180, and just list out a bunch of these. And then for the next one, see if we can find any matches. So I'm looking at 50, 100, 150, and then of course we will see 150, 150. So the least common multiple of 15 and 50 is 150. Effective, yes. Quick, efficient, and painless, no. This is not a great way to find the least common multiple of two numbers. We actually got kind of lucky. These were nice numbers. There's a better way, and that's what I want to demonstrate right now. It actually has to go back to our prime factorization idea. So I'm going to do this in, let's go green. 15, if we break it down into its prime factors, 3 times 5, right? We could make a tree if we need to. 15 is 3 times 5. 50, I'll change colors to dark purple. Well, I know that's 5 times 10, and 10 is 2 times 5. So this is 2 times 5 squared. 50 is 2 times 25, 5 squared. So broken down into their prime factors, how we can get the LCM is going to be, we're going to take each prime factor to the highest power that we see there in either one of our two numbers. So I like to go in order. I see a 2. There's a 2 in purple, there's no 2 in green, so 2 to the first, because that's what it is, that's all I see. Times 3 to the first, I just see a 3. Times, and then if you look, we've got a 5 on top and a 5 squared on bottom. What is the biggest power? Times 5 squared. So that's 2 times 3 is 6, times 5 squared is 25. 6 times 25, 150. And I used my space pen there because I want it to kind of stick out. That's probably a much better and more efficient way to find LCM of two numbers. If they're two easy numbers, sure, list them out. List them out on your paper, list them out in your head, find it. But what if the numbers were bigger? What if they're in the hundreds, the 200s, the thousands, the tens of thousands? I don't want to be stuck trying to multiply those in my head, list them out. This is a systematic way to find the LCM that'll work every time. So that's great. What if it's not just primarily numbers though? We've got 14x squared y, we've got 21y cubed. I want the LCM. Let's do what we did with those numbers. 14 is equal to 2 times 7. And 21, I'm just looking at the numbers right now, is 3 times 7. So what is my LCM then of the numbers? I have a 2, and it's just 2 to the first. And I have a 3, and that's just 3 to the first. And then I have 7 to the first on top, 7 to the first on bottom. It doesn't matter which one we take, it's just 7 to the first, because that's the highest power we see. 2 times 3 is 6, times 7, 42. It looks like the LCM of the numbers is 42. Variables are really easy. What's the highest power of x's that we see? Well, we have x squared here and nothing else over there, so I'm going to say x squared. And then what's the highest power of y's that we see? Y to the first, y cubed. I'm going to take the highest one, y cubed. 42x squared y cubed is the least common multiple, the LCM of these two expressions. One more, just showing you, kind of ramping up the difficulty. What if it's just like polynomials? So we have, find the LCM of x squared minus 2x and x squared minus 4. Well, I'm going to come over here and say this first one is x times x minus 2. I could factor out an x. Again, factoring super important. That's x times x minus 2. And then the second polynomial, x squared minus 4, difference of two squares, x plus 2, x minus 2. So again, we're just factoring like every time. When in doubt, factor. So what is my LCM of these two polynomials? Well, we're going to take each factor and take the highest power that we see for it. Just x. I see x to the first on the left, and no just x's anywhere else. You might be saying, what about that x and the x plus 2 or the x minus 2? They're connected. Remember, a polynomial is one factor in this case. So we have x times x minus 2 to the first and x minus 2 to the first. It appears in both red and blue. So we know it's just x minus 2. And I'm going to try to like show that either one of those worked because they were both to the first power. And then we had an x plus 2 on the other one. X plus 2 to the first was the highest power we saw. There's our LCM. Again, kind of like I said in the last video, I would just leave it there. It's going to be more convenient when we're graphing if we don't multiply it all out. Just leave it x times x minus 2 times x plus 2. So I started this off by saying we're adding and subtracting rational expressions in this video. Why do I start with LCM? Because there are going to be times we might need this to find a common denominator. We need a common denominator. We want it to be the least common. So our fractions are simplified, our rational expressions are simplified. So we're going to need to sometimes find the LCM of two denominators. So let's start looking at how do we actually add and subtract rational expressions. We'll start with a pretty simple one. 6 over AB plus 8 over A. We're trying to add them. We need a common denominator. We don't have a common denominator. So the question you want to ask yourself is, what could I multiply one or both of those rational expressions by to get a common denominator? And in this case, we can see probably just by looking at it that if we multiply my second expression by b over b, remember we got to multiply by the same on top and bottom, well, that actually is now going to give me a common denominator. So 6 over AB plus 8b over AB, common denominator. Now we can combine the numerators, combine like terms, put them over one. Denominator, in this case, it's just going to be 6 plus 8b over AB. Find a common denominator, then you can combine those numerators. Tiny bit harder one, not crazy. We're still not to factoring, we're just looking at some monomials on bottom, but we have 5 over a squared b minus 7a over a squared. And again, we're trying to get a common denominator. So 5 over a squared b minus 7a over 5a squared. Now, ask yourself, what is the LCM, the least common multiple for my denominators? How could I make them have the same denominator? And I say, well, the one on the left is missing a 5 on bottom. So I'm going to multiply by 5 over 5 on the left. Now my left denominator will be 5a squared b, which is pretty close to what I need on the right. On the right, I have 5a squared. We'll multiply by b over b to get 5a squared b on both denominators. Hopefully you see that. We get 25 over 5a squared b minus 7ab over 5a squared b. And now that they have a common denominator, we can write it just over a single denominator. So adding and subtracting, we need that common denominator. We'll do one more of these and then one last set of problems and call it good for this lesson. A over a minus 4 minus 3 over 4 minus a. This is similar to something we saw in 8.1. A minus 4, 4 minus a. So close, but they're not the same. They're not common. The signs are different. On the left, we have positive a minus 4. On the right, we have positive 4 minus a. How can I flip the signs of one of those? Well, let's multiply by -1 over -1. Because if you remember from the 8.1 video, multiplying by the negative just changes all the signs. We get -a plus 4. And then we get 4 minus a. And take a look at those two denominators. Are they the same? Mathematically, yes. Right? -a plus 4, we could just flip their order and it would be 4 minus a. So I think this is looking pretty good. We now have common denominators. I'll write it as such. So I'll say -a over 4 minus a minus 3 over 4 minus a. And we could just write this then as -a minus 3 over 4 minus a. So you guys see this multiplying by a -1 trick. It helped us in the 8.1 section for multiplying and dividing, so that sometimes we could maybe cancel some stuff out if the signs were flipped. Now we're seeing it can help us find a common denominator if we need to, if some signs are flipped in our denominator. So just a quick example of that. So these 3 problems on the screen, I'm hoping they make sense. I'm hoping you're saying, okay, so on the first one, oh, the second rational expression is just missing a b on bottom. Let's multiply by b over b. And then on problem number 2, I needed to hit the left-hand one with a 5 over 5, hit the right-hand one with a b over b. And then the third one, we multiplied by that -1 over -1. We multiplied the left rational expression by that to flip the signs in the denominator, get us our common denominator. That's what adding and subtracting boils down to, common denominator. All right. One more set of problems then. 5 over r plus 7. And I'm hoping that everyone agrees with me. We could write that as 7 over 1, right? There's always a little invisible over 1 here if we don't see a denominator. So 5 over r plus 7 over 1. What do we need to multiply by to get a common denominator? Do it, simplify, put it over the same denominator. I'm going to pause mine, do it, and then I will unpause. All right, right here, I multiplied the right-hand rational expression by r over r to give me 5 over r plus 7r over r, which equals 5 plus 7r over r. Final answer. Here's another one. 3 over 4q minus 2 over 5q minus 1 over 2q. I'm going to ask you to try to work this one out from the top. Yeah, there are 3 terms there, 3 things that are involved in this subtraction. We need to get them all to have a common denominator, figure out what we can get all those denominators to, multiply by what you need, and then when you're done, unpause this video to see how I did it. All right, so on this one, the numbers are pretty easy on bottom. They all have a q to the first. So we're set there. We just need to make the numbers match. 4, 5, and 2. This is one of those LCM problems I could probably just do in my head. 5, 10, no. 15, no. 20. I could get 4, 5, and 2 to 20. 20 is the LCM of those numbers. To get them to 20, I'm going to multiply the first rational expression by 5 over 5. Gets me to 20q. The second one, I'm going to multiply by 4 over 4. Gets me to 20q on bottom. The third one, I'm going to multiply by 10 over 10. Should get me to 20q, meaning that I now have 15 over 20q minus 8 over 20q minus 10 over 20q. And since they all have a common denominator, we can put them over that same common denominator and then just simplify. 15 minus 8 is 7, minus 10, negative 3 over 20q. Hoping that one looks good. Let's start getting into some factoring then. We have 2 problems left. They're going to give us a little bit of practice with factoring. Y over y plus 3 minus 6y over y squared minus 9. Pause the video, but my hint for you, my advice for you is, can we factor one or more of those denominators and then see what we would need to multiply expressions by to get a common denominator? I'm pausing. I'm going to give you some time, and then unpause and see if my explanation makes sense. All right, let's do this. Y plus 3 on left. Nothing really to factor. Linear, nothing to pull out. 6y on top on the right. No, but y squared minus 9 is that difference of 2 squares. Y plus 3, y minus 3. So what do I need to do to get these a common denominator? Well, it looks like if I multiply the left-hand one by y minus 3 over y minus 3, look at the denominators now. Y minus 3, y plus 3, y plus 3, y minus 3, they're multiplied, they're the same. Now we're in business. Let's carry this out. So y squared minus 3y over, and I'm just going to write them in the same order, y plus 3, y minus 3, minus 6y, we didn't multiply that one by anything, y plus 3, y minus 3. So now I can put those over the same denominator since it is common, y squared minus 3y minus 6y, all over y plus 3, y minus 3, y squared minus 9y over y plus 3, y minus 3. And it's a good idea at this point to try to factor, even your final answer. See what you get in case there are things you can cancel out. On top, I see I can pull out a y minus 9, y plus 3, y minus 3. And there aren't any common factors on top and bottom that I can just divide out. So in this case, that last factoring wasn't necessary, but we don't know it until we do it. And so we get y times y minus 9 over y plus 3, y minus 3. That's how we would do this factoring, adding, subtracting problem. All right, last one. And then I'm gonna, after that, I'm gonna just set up the next lesson by reminding you of something. But this is the last adding and subtracting problem that we're working. What my challenge for you is is to write this problem down, 5 over x squared minus 3x minus 28, plus 7 over 2x minus 14. Solve it front to back. I'm going to do it off camera. I'm going to pause and work this one out, and then we can both unpause and compare the work. All right, walking through my work on the screen here. In red was my original problem, what I started with. I factored that bottom left denominator, so bottom denominator, the left denominator into x minus 7, x plus 4. I factored the right denominator into 2 times x minus 7. I just pulled out a 2. Then I said, what do I need to multiply these rational expressions by to make them have a common denominator? The left-hand one was missing a 2. It had the x minus 7, x plus 4. I needed to multiply by 2 over 2. The right-hand rational expression was missing the x plus 4. I needed to multiply by x plus 4 over x plus 4. So when I did that on the right-hand side of the screen, now in purple, I kind of multiplied it out. We get 10 over 2x minus 7, x plus 4, plus, and then distribute the 7, 7x plus 28 over 2x minus 7, x plus 4. Meaning common denominator, we can write them over the same one, 10 plus 7x plus 28 over our denominator, giving us 7x plus 38 over 2 times x minus 7 times x plus 4. Final answer. Adding and subtracting rational expressions comes down to, can you get a common denominator? Sometimes that's like this problem, and you just need to multiply by numbers. Sometimes if we're working with polynomials, you're going to have to factor, and then you're going to figure out what factors do I need to multiply by. But either way, I'm confident you have the skills to carry out these operations and simplifications. So one other concept that I just want to tease before calling it good for this video, and I mentioned it sort of at the beginning of the 8.1 video. Now I'm mentioning it at the end of the 8.2 video because we're going to see it here very shortly. I want to know where this rational function is undefined. Where does it not exist? Well, if you remember, it doesn't exist when the denominator equals 0. So if I'm trying to find where it's undefined, I'm just going to start by saying, where does the denominator equal 0? And when you see a quadratic like that, you should just internally be busting a gut to say, let's factor that. X squared is x times x. Signs are different, plus minus. Multiply to be -4, add to be +3, plus 4, minus 1. So for what values of x is our function undefined? When x is -4 and 1. Those are the two x values that would cause us undefined. This is important because it's going to play a part in 8.6 when we're solving rational equations and trying to figure out if our answer actually works or not. This is important because in 8.3, when we're graphing, we need to know where are there breaks in the graph. We're going to learn all about how to graph those in 8.3, and they always happen where f of x is undefined. We see these discontinuities, these breaks in the continuous nature of the graph. But this is more just a tee up to the next video. For now, 8.2 was mainly about adding, subtracting. I just wanted to get that one idea further ingrained in your head because the more times you hear it, the easier it'll sink in when we actually get to it. You're going to have some practice problems, adding, subtracting, finding common denominators. Hope those go well. Circle ones that you have questions on so you can ask me. But that is all for section 8.2. I will see you guys in the next video.